Why is the periodic table organized as it is today? Why isn't it organized alphabetically, or by date discovered, or by the abundance of it found in our atmosphere? It was seen that as more and more elements were being discovered, chemists tried to find a way to organize them that would show how their properties were related. A chemist named Dmitri Mendeleev discovered the key. Mendeleev was a card player. He wrote the names, masses, and properties of the 63 known elements on playing cards, and shuffled and dealt them again and again, looking for a good way to organize them. Eventually, he realized that when elements are listed in order of their mass, their properties are periodic. The table contains 118 chemical elements whose discoveries have been confirmed. There are 18 groups in the periodic table. The elements in a group have similar physical or chemical characteristics of the outermost electron shells of their atoms. All of the rows go left to right. Every element in the top row has one orbital for its electrons. All of the elements in the second row have two orbitals for their electrons. This continues the whole way down the periodic table. There are progressively longer periods further down the table, grouping the elements into S, P, D, and F blocks to reflect their electron configuration. Electron configuration is the distribution of electrons of an atom or molecule in atomic or molecular orbitals. For example, the electron configuration of cobalt is 1s2, 2s2, 2p6, rs2, 3p6, 3d7, 4s2, or just argon 3d7, 4s2.
The alkali metals are a grouping of chemical elements in the periodic table with very similar properties. They are all shiny, soft, and highly reactive metals at standard temperature and pressure. An example of an alkali metals is lithium, a soft silver metal that is the lightest and least dense of the metals. Lithium is also highly reactive and a flammable compound. Lithium has several industrial applications, including alloys used in aircraft and lithium batteries. The other alkali metals are potassium, sodium, cesium, and francium.
The alkaline earth metals are a group of chemical elements in the periodic table with very similar properties. They are all shiny, silvery white, somewhat radioactive metals at standard temperature and pressure. An example of an alkaline earth metal is magnesium. It is the eighth most abundant element in the Earth's crust. It burns with a brilliant white light, making it a useful tool in flares. Magnesium's high burning temperature also makes it a useful tool for starting emergency fires. The alkaline earth metals are beryllium, magnesium, calcium, strontium, barium, and radium.
The transition metals are any group in the D block of the periodic table, which includes group 3 to 12. All elements in the D block are metals and conductors of electricity. Transition metals possess a high density and high melting points and boiling points. The transition metals also contain the three magnetic metals, iron, cobalt, and nickel. An example of a transition metal is iron. Iron is the most common element by mass on planet Earth. Iron metal is strong, but is also quite cheap, therefore it is the most common metal in use today. The halogens are 5 non-metallic elements found in group 17 of the periodic table. All halogens have 7 electrons in their outer shells, giving them an oxidation number of -1. An example of a halogen is iodine. Iodine is primarily used in nutrition. It is required to synthesize thyroid hormones. The halogens exist at room temperature in all 3 states of matter. Iodine and astatine at room temperature are solids. Bromine at room temperature is a liquid, and fluorine and chlorine at room temperature are gases. The noble gases are a group of chemical elements with very similar properties. They are all under standard conditions, odorless, colorless, monatomic gases with very low chemical reactivity. The 6 noble gases that occur naturally are helium, neon, argon, krypton, xenon, and the radioactive radon. An example of a noble gas is neon. Neon is a very common element in the universe, but rare on Earth. A colorless noble gas under standard conditions, neon can be used in advertising signs. It is extracted from air, where it is found in trace amounts. The atomic radius is 1/2 the distance between the nuclei of 2 atoms. Atomic radius decreases from left to right within a period. This is caused by the increase in the number of protons and electrons they cross a period. 1 proton has a greater effect than 1 electron, thus a lot of electrons will get pulled towards the nucleus, resulting in a smaller radius. Also, atomic radius increases from top to bottom within a group.
Ionization energy is the amount of energy required to remove an electron from a neutral atom in its gaseous phase. The lower this energy is, the more readily the atom becomes a cation. A factor that affects ionization energy is electron shielding. Electron shielding describes the ability of an atom's inner electrons to shield its positively charged nucleus from its valence electrons. Ionization energy of the elements within a period generally increases from left to right. This is due to valence shell stability. The ionization energy of elements within a group generally decreases from top to bottom. This is due to electron shielding.
Electronegativity is a chemical property that describes an atom's ability of attracting and binding two electrons. Electronegativity measures an atom's strength to attract and form bonds with electrons. As you move to the right across a period of elements, electronegativity increases. As you move down a group, electronegativity decreases. The most electronegative element is fluorine.
Despite being a relatively small table, it is very complex. Everything on Earth, in one way or another, is created using different parts of the periodic table.
There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.